So please, Aya, the floor is yours.
Great. Thank you for the introduction, and thank you to everyone for coming to listen to my talk, especially the ones who are in Europe where it's quite late. So today I'll be talking about astroseismology with multi-taper methods. And this is an astrostatistics project that's done with Gwen Eadie, Joshua Spiegel, and David Thompson at the University of Toronto and Queen's University. And I also want to thank Connie Ertz, who has been advising us with respect to this project. So I want to direct your attention towards the image that I have at the top. While it looks like abstract art, that's basically a time series of a star, and we're seeing some oscillations there. And the study of these oscillations is what we're interested in, that is astroseismology. And as I said, this is data in the time domain, and that's the domain I'll be talking about, time series analysis through multi-taper methods. So a quick overview of the talk. I'll first be motivating our work. Then I'll be talking about the problem, which is a very fundamental problem in time series analysis. Then the current methods, particularly Lomsky-Scargill periodogram and its limitations, and the solution we propose to this problem. And finally, I'll wrap up with how this allows us to have better understanding of planets, stars, and the Milky Way. So coming to the motivation, the star we know the most about is the sun. And we know that the sun has this outer convective zone and this radiative zone in the center near the core, where we see gravity modes, and in the outside we see pressure modes. And we know that this is true for high mass stars as well, where the zones are flipped. So we have convective cores and radiative envelopes. And this means that we see more dominant gravity modes near the envelope. And this leads to the different astroseismic oscillations. And if we put it all together on the astroseismic HR diagram, we see that there's lots of oscillations to study. And we, in particular, are interested in the pressure modes, specifically for solar-like oscillators. And this is because we are working in the domain of galactic archaeology. So I'll talk more about that later. So the problem we're dealing with is, as I said, very fundamental. How do we measure all these types of oscillations that we see in stars, given time series data? So we're going from the time domain to the frequency domain. And in the frequency domain, we know that there's a lot of information relating to stellar activity. We know that there are signatures of exoplanets as well, even though they're not shown here. And in particular, we know that there's acoustic modes or the oscillations that we can study by measuring the parameters like delta nu and nu max, which give us mass and radius through scaling relations. And my work is how do we actually get more precise masses of these stars, and from that get more precise ages to be actually able to map the chemodynamical evolution of the galaxy. So the current methods that are used in this domain face some challenges. The two of them are irregular sampling and statistical inconsistency and bias. And I'll talk about each of them and our solution to these. So in particular for irregular sampling, we know that, for example, in a Kepler time series, we have lots of gaps, and even beyond these gaps in smaller sort of zoomed in regions that I'm showing here, there's also some missing data. And this is actually worse for ground-based data. So we see more missing and data and irregular sampling there. And generally, the solution is to use the Lomskargil periodogram, which falls under the class of sort of non-parametric spectral estimators, where we don't plug in any parameters to get the spectrum of a particular time series. And I'm not going to go into the details of this equation, but the idea is that it's kind of like a Fourier transform, but with some modifications. But the thing that we wanted to tackle was that if you go back to the Lomskargil paper, they were interested in a very specific signal, specifically a periodic signal hidden in noise. And most of the tests in the paper are related to white noise. It's basically so that periodogram analysis and least squares fitting of sine waves is the same for Lomskargil periodogram. And so what we were trying to ask is that, does this apply to quasi-periodic pressure modes, which we know are not strictly periodic? And that's where we basically updated the previous approach of using a Lomskargil periodogram to what we call the non-uniform fast Fourier transform periodogram. It's hard to see in this particular figure, but both of them agree quite well with each other. So what is this NUFFT periodogram? Our proposed solution is to generalize the classical periodogram using non-uniform fast Fourier transform without making any modifications like are done to the Lomskargil periodogram. And our goal here is to be able to not just detect strictly periodic signals, but quasi-periodic signals as well, as accurately as possible. Now, the problem here is that you might ask, what is the corresponding distribution of this periodogram estimate? And this is because the Lomskargil periodogram was designed so that the even sampled chi-square distribution of the classical periodogram is maintained in irregular sampling. And so if we do this very simple modification, we do not get a chi-square 2 distribution, but we do get that if we handle gaps in data separately, and if we have quasi-regular sampling, that is, our sampling is quite close to regularity. And this is the kind of data we deal with when we're looking at Kepler time series. And so that was our proposed first modification, is to reduce the changes made to the classical periodogram. Now, the second thing we wanted to tackle was statistical inconsistency and bias. So what inconsistency means is that you have an estimator. So for example, the Lomskargil periodogram, and the variance of that estimator itself does not tend to 0 as the number of samples in your time series tends to infinity. And what that means is that no matter how many samples you have, your periodogram estimate is going to be noisy. And then the second part is about bias. And what that means is that there's leakage of power from one frequency to another, or spectral leakage, which leads to a biased estimate. And to kind of show you how this works, I'm going to use something called pseudo windows. So pseudo windows, essentially, what they do is that they take the time sampling of a time series. So you can see on the left here, the Kepler time series of a red giant star. And then I take the same times, but just convert the time series to a synthetic time series with some sinusoidal signals. So I have 2 sinusoidal signals here. And now I see the spectral response of this synthetic signal. And what I'm showing here at the bottom is in log space, this power spectral estimate of the synthetic time series. And you can see that the true power spectrum should just be 2 delta functions at the frequencies that we've added with some amplitude. But instead, we see a lot of leakage of power. In the inset here, I'm basically showing this in linear scale. So you have a better sense of how strong the leakage can be and how that can actually make you think that there's a signal present when it's actually an artifact of your time series itself. And we found that this is true for both the Lomskargil and the modification we've proposed, that is the NUFFT periodogram. And so we tried to combine our NUFFT periodogram with multi-taper spectral analysis to be able to solve this issue of leakage and also the variance of the spectral estimate, which refers to inconsistency. So let's look at how that works. Essentially, instead of just taking the fast Fourier transform of the data, so xt times this exponential factor is the FFT for an evenly sampled time series. Instead, we multiply that with some taper in the time domain and then compute the transform. And these tapers that we use are called Slepian sequences or discrete prolate spheroidal sequences. And they look something like this, as I've shown in the plot to the right. And this is, again, something that was suggested in Scargill's original paper. They suggested that we can use tapering to improve upon the difficulties that Lomskargil periodogram faces. And we propose that because we are dealing with irregular samples or quasi-regular samples, we use a cubic spline interpolation of the tapers to the unevenly sampled data points xn tn. And to show you all of this in a visual format, basically I take the time series as shown to the left. I multiply it with the individual tapers of these Slepian sequences. And then I get a tapered time series in the time domain. I then compute periodograms for each of these tapered estimates and then eventually combine them. And that's where the multi-tapering comes in. And you can actually average them because these are sort of eigen or orthonormal to each other. So you can think of them as kind of eigenfunctions. And through that, you can get an estimate that has lower variance. So your noise is reduced and your spectral leakage has reduced as well because the tapers reduce the leakage. And to show how this works, I'm presenting this plot here where at the top, again, I have the spectral response of my pseudo window that I'd shown before. And you can see that the Lomskargil had a lot of spectral leakage, same as the NUFFT periodogram here in black. But when we taper this, the leakage actually reduces quite significantly. So here you can see in blue that the little bump has gone down, and you can see that in the linear scale as well. And one thing I want to highlight is that you can add more and more tapers to your estimate, but there's a trade-off between frequency resolution and number of tapers you can use. So the more tapers you add, your variance of the estimate will reduce, so you will get a less noisy estimate, but your frequency resolution will keep getting worse. So this is what you see here. I have 2 tapers, and the bandwidth of this has now increased. So you just have to make sure that you use the bandwidth that follows your physics problem. So to show how this looks like for the Kepler time series itself. So in black, I'm showing the Lomskargil periodogram. of the Kepler 91 time series. And in orange, I'm showing the multi-taper NUFFT, multi-taper Lomskargel estimate. And you can clearly see that the variance has significantly reduced. And to the top right, you can also see that there's a confidence interval that you can get with multi-tapering because you can jackknife over each individual tapered estimate. And the same is true for our NUFFT periodogram. In gray, you can see the NUFFT periodogram, and in blue, you see the multi-tapered version of that periodogram. And all of this sort of converges to the idea that we can get better estimates of pressure mode frequencies and other characteristics of these pressure modes like widths and things like that. And one other part of the project that we were interested in looking at is that can this help in exoplanet detection? Because we know in the power spectral estimate, there are signatures of exoplanets present. And before I actually move on to the multi-taper F-test part, which talks about exoplanet signals, I just wanted to ask if anyone had any questions, because I've gone over quite a lot of content. If not, I can keep continuing. Okay, so till now, okay, I see something in the chat. Okay, so far so good, great. Please interrupt me at any point if you have any questions. But yeah, the next part will focus a little bit on exoplanets. Here I'm showing a very simple picture of what an exoplanet signal might look like. Essentially, you have sort of this stable light curve, which is just coming from the star. And then you might have a dip because an exoplanet is transiting. And then again, you'll have a dip at the period of that exoplanet. And if you take a fast Fourier transform or a periodogram estimate of a time series like that, you'll get something like this, where you have this periodic signal at the frequency of that exoplanet, but also at multiples of that frequency. So that's why you see it at 3.2 and so on. And this differs from other types of signals. So for example, at the top, I'm showing just a simple sinusoidal signal. And that sinusoidal signal basically should show up just as one single peak in the frequency domain. And this is something that might resemble, for example, coherent modes. And then at the bottom, I'm showing basically a harmonic oscillation that's damped. And you can see that in the frequency domain, it has some sort of width, and that width represents the damping. And so these are the different types of signals we're dealing with. And our idea was that by using something called the multi-taper F-test, can we actually distinguish between these different types of signals directly in the frequency domain without doing a lot of other modifications. And so the multi-taper F-test basically tests whether there's a purely periodic component present at frequency F or not. And by purely periodic, I mean the first type of signal here, which is strictly periodic. But it could also mean an exoplanet signal, but only the single frequency here. So we are dealing with sort of types of signals in the first two panels. And how that works is that, again, I go back to the same Kepler time series, Kepler 91. I have computed the multi-taper NUFFT periodogram for that time series that I show to the left. Then I've computed the F statistic for each and every frequency of this periodogram. And that's what I show here to the right. And this was computed using this formula here. I'm not going to go into the details of this because it's a bit involved, but I'm essentially using something related to the tapers to compute this F statistic. And then essentially we test this F statistic, which should ideally follow an F distribution if it satisfies the null hypothesis that there's no periodic, purely periodic signal present at frequency F. But if there is a periodic component, then it should fall in the rejection region with some level of confidence. So here I'm using 0.05 as the confidence level. And to the right here, I'm just showing the p-values corresponding to the F statistic. And you can see there's a lot of frequencies that fall beyond the 0.05 confidence level or rejection level, sorry. And so are we really detecting that many strictly periodic signals, or are these false discoveries? And this is where we use something called multi-hypothesis testing. The idea is that if you're testing if a particular test is true at one single frequency, that's fine. But if you're doing it over thousands of frequency, then you might run into the problem of having too many false discoveries. And so we use some correction factors. Again, I'm not going to go into the details of that. But we use Benjamini-Hochberg and Bonferroni corrections to correct for this problem of false discoveries due to too many tests at one time. And then finally, we are left with just 4 different signals, which I'm showing here to the left in black. And the interesting thing we found is that by doing this procedure without feeding anything into the model about the physics, we found that 3 of those components actually coincided with exoplanet harmonics. We think that our method is actually able to find out these exoplanet harmonics as purely periodic and not the P modes, because these P modes are quasi-periodic or damped oscillations. And then another thing we tried with our F-test was to play around with its variance. What that means is that we get a particular estimate of a frequency at which we have a purely periodic signal. And that frequency has some variance or some uncertainty. And that variance actually is given by this equation. Again, I'm not going to go into the details of it, but essentially it's 1 over t squared proportionality multiplied by the signal present at that particular frequency f naught divided by the signal present at that particular frequency in the line component. And the top is the noise. And what that means is that the variance is inversely proportional to t cubed. And so if I reduce the length of my time series, the variance of my frequency estimate should not increase much. And what that means is that I can actually go and split my time series into different sections and compute the F-test for each individual section and see whether a particular signal is changing in frequency or not. And this can tell us whether the frequency is truly stable or not. And this also helps because I can actually remove big gaps in the data. So this is what I've done here. I again took the same Kepler time series, split it into 3 big, fairly big chunks, computed the periodogram for each of them, and then calculated the F-test with multi-hypothesis testing. And what we find is that for each of these individual sections, we get the frequency of the exoplanet, and the exoplanet frequency is quite stable, showing us that this is actually a strictly periodic signal. And another thing I want to highlight is that we actually get the variance of the F-test, as I was showing before. And that is quite small compared to the Rayleigh resolution. So the frequencies we detect are very precise. So we can get a very precise estimate of the exoplanet itself, period itself. And then we use the variance of the F-test to also try to look at pressure modes. So here I'm showing at the bottom one particular mode, so nu with n equals 9, L equals 2 for the same time series. And another mode, n equals 10, L equals 0. And I'm showing basically for the time series that we have. If we use the individual small chunks, so here I'm using chunks of order like 60 or 90 days. And this is the order where we expect the pressure modes to not damp very significantly. So I'm trying to see whether there's an evolution in the pressure mode itself with different time chunks. And as you can see, the frequency does change quite significantly over different time chunks. In some of the time chunks, we can't even detect one of the modes. And in this one, we can detect either. So this is actually showing that we do see shifting P modes when we split our time chunks into individual sections. So all of that basically told us that we can detect exoplanet periods very precisely, and we can actually look at the evolution of pressure modes in terms of their frequencies. Now I go back to the main problem that we were dealing with, that is actually estimating these modes that we've been trying to understand. And here I'm showing an example simulated time series. In black is the power spectral estimate of that simulated time series. The orange one is the sort of true PST that we used for the simulation. And in green, I'm showing the multi-taper estimate that we get for this simulated time series. And you can see that the multi-taper estimate agrees with the true PST quite well as compared to the Lomskargil estimate. And then at the bottom, I'm just showing that if I increase the number of tapers, the resolution might get a bit worse, but it will still be able to detect these frequencies quite well. So this kind of showed to us that this works in principle. And I just want to highlight that this comes from the fact that the distribution of the multi-taper periodogram is chi-square distributed, but with higher degrees of freedom. What that means is that for the Lomskargil, you see the distribution is exponential because it's chi-square distributed with 2 degrees of freedom. Whereas with multi-taper, as you increase the number of tapers, your degrees of freedom of the distribution becomes 2K. And slowly the distribution of your periodogram comes closer to a normal distribution. And that means that you actually get values of your power spectral estimate quite close to what the true value is. This is what is being shown in this diagram. To the top left, I'm showing the Lomskargil periodogram of the Kepler-91 time series. And I'm showing a smooth version of this Lomskargil periodogram. And you can see that the Lomskargil has a lot of noise. And then after smoothing, you can actually use something called PBJam, which is a Python package for doing peak tagging. And PBJam essentially fits for L equals 0 and 2 modes in your spectral estimate. And if you use multi-taper in place of the Lomskargil periodogram, you see that the variance has reduced significantly. So the smooth version actually looks quite similar to the multi-taper estimate itself. And one question I often get from people is that if we can just smooth the Lomskargil periodogram, why do we have to do multi-tapering? The problem with smoothing the Lomskargil periodogram is that when you smooth over the periodogram, you're smoothing over the leakage as well. So you're actually making the estimate more badly biased by averaging it. And this is something that is tackled by multi-tapering. And because of the lower variance and lower leakage, basically the likelihood that we use to fit for the modes changes. The main change is basically there's a factor of K to the likelihood, because your chi-square distribution has now changed from 2 degrees of freedom to K degrees of freedom. And what that means is that all the estimates you get from Lomskargil, the uncertainty will actually be divided by root K when you use multi-tapering. And so that gets me to the conclusion, which is that we actually get more precise delta nu and nu max estimates because of this reduction of uncertainty. So you can see here the standard deviation for delta nu and nu max when you use MT-NU FFT with PBJam, when you use Lomskargil with PBJam, and when you compare it directly with the APOCAST2 estimate itself. And you can see that in all 3 cases, the multi-tapering is the most precise. And what that means is that not just the delta nu, nu max parameters are precise, but the actual mode estimates are precise as well. So here at the top, I'm showing in red, the LILO box estimates for these modes in the literature. And you can see with PBJam and Lomskargil, the uncertainty is reduced. And with PBJam and MT-NU FFT, it's reduced even further. And so all of this means that we get more precise masses of stars. And also we can study the internal structure of stars better. At least that's the hope of this work that I'm showing right now with one case study. And then eventually the idea is that if we actually use some, assume some physics and actually compute ages for these different periodogram estimates, so with multi-tapering, with Lomskargil and the APOCAST2 estimates, both corrected and uncorrected, you see that there's actually more precise age estimates with multi-tapering. And this goes back to my problem of galactic archaeology. If we could get more precise estimates for a lot of stars, that will help understand chemodynamical evolution better. And that gets me to the end of my talk. The takeaways are that we are working towards improving our method, both from the statistical point of view and the astroseismic point of view. We only did one particular case study. We want to expand this to a lot more stars. We also want to go beyond using PBJam, which assumes some input physics. We actually want to do better modeling. And we also have some ongoing work on extending this to high mass stars. So this goes back to the time series I showed in the first slide. And whether we can use multi-taper F-tests to improve upon pre-whitening, because we get very precise estimates of purely periodic modes. So we could essentially look at gravity modes and coherent modes that way. I also have a Python package for all of this analysis. So all the figures that I showed right now were made using this package. I'm currently developing the documentation and testing for it, but you should be able to use this method on your own time series data very easily. And thank you. I'll take any questions you might have.
Excellent. Thank you very much, Jaya, for a very interesting talk and a lot to digest. Um, but very interesting. So let's open it up for questions. So if people have questions to ask, just raise your hand. And we have Giovanni first.
I can't hear you.
No, me neither. Can you try it again, Giovanni?
Can you hear me now?
Yes.
Yes.
Okay. Sorry. I know about this, and sorry. So a very interesting talk. Thank you very much. I had a small question about what you just showed at the very end. Your uncertainty estimates, basically. You showed that clearly you spent a lot of work and testing into to get a better, more accurate delta nu and nu max. And I see you reduced the uncertainties by like a factor 3. But in the end, you only have a 0.5% improvement on the uncertainty on the age. So from this here, yes. And then a few slides later, you showed the age, Lomscargill versus, yes, this one. How come, what is basically diluting your increase in precision so that it's not so obvious here anymore?
Right, that's a very good point, and that's actually something that we address in the paper. I will put that in the chat just so that's useful. But the idea, the problem behind sort of having more significant reduction in uncertainty in delta nu nu max and not the same in age comes from how the uncertainty propagation works. So if you're propagating uncertainty from delta nu nu max to mass and then to age, you also have to consider effective temperature uncertainty and also have to consider FEH uncertainty. And if you look at how, if you just use a simple scaling relation, you can look at the factors of delta nu nu max and T effective. And the problem is that the relative uncertainty of T effective dominates when you go to really precise delta nu nu max estimates. And that dominating factor makes it so that even though you have significant reduction in delta nu nu max, your mass and age doesn't reduce in proportion. But we think that if we're looking at stars that have not as precise delta nu nu max, so if the signal to noise ratio is not as good, then maybe the relative uncertainty will be like the reduction will be more, and then that will improve ages more significantly. Does that answer your question?
Yeah, definitely. I thought that increasing the accuracy of the precision on 2 of the 3 ingredients would have a larger impact. So, okay, I'm sorry.
Yeah, I think it's, as I said, it's the relative uncertainty. So if you look at sort of uncertainty in delta nu divided by delta nu versus uncertainty in effective temperature by effective temperature, it's an order of 0.1 to 0.01 kind of difference.
Okay, thank you.
So Patricia had a question in the chat. So is the choice of taper a critical issue?
Yeah, so that's again a very good point, and I think I had that in my end slide. There's a reference here, the paper by Charlotte Halley, and they try to essentially optimize the parameters NW and K, which oops, I'm not able to move this, but the 2 parameters, so bandwidth NW and K is essentially usually set to 2 times NW minus 1. So the only parameter you need to set is the bandwidth. But it is critical because if you use a very large bandwidth, as I said, you're going to lose out on frequency resolution. So you do not want your bandwidth to be so big that you're looking at basically modes that are combined together. So this should be somewhat informed by your physics in a little bit. We are trying to see if statistically we can actually improve this, but it's an ongoing problem in the statistics domain as well. So I do not have the perfect answer for how to do that.
Okay, thank you, Arya.
And Connie, do you maybe want to ask your question, or should I read it?
Okay, yeah, I can ask it, but it's literally in the chat. Hi, Arya, thanks for a good talk. So you quickly browsed over the step that you do with jackknifing. Maybe not everybody on the talk knows what that is. So can you explain that and tell us why this step, why you use this step compared to general bootstrap and how it helps you? That was my general question.
Yeah, no, that's another good point that I did not go over much. But so when I do jackknifing, I'm essentially, as I said, I have individual multi-taper spectral estimates. So as I showed here, these individual estimates give me the final periodogram. But if I want to jackknife these, then what it will mean is that instead of using 3, I can use 2 out of the 3 with different combinations. So I can use the first 2 estimates, combine them together. I can use the last 2 and the first and third to get 3 different estimates of the periodogram itself and get a sense of what the confidence interval of the periodogram estimate is. And I'm not sure if we address whether this is like the best method to do it. Like as Connie is mentioning, you can do bootstrap, which kind of like the name itself kind of explains what you're doing. You're like strapping one of it out and trying to estimate again the uncertainty in your periodogram. So that is again a very good question, something that we haven't looked at yet, but maybe we can try to see whether there's a way to compare different methods to get confidence intervals.
Okay, thank you.
Okay, any other questions? Please raise your hand. Christopher Lindsay.
Hi, thanks for a great talk. I'm Chris Lindsay. I'm a grad student at Yale. I was just wondering if there was any plans you had of adding this functionality directly into some of these peak bagging codes, and if you ran any tests on the potential computational slowdown of this analysis versus a standard Lomskargel.
Yeah, so for the addition of something like this to peak bagging codes, it's definitely possible. We essentially swapped Lomskargel to multi-taper NUFFT in this work, but we haven't really talked to the PBJam people yet, but I would love to talk to people and get a sense of how we can try to combine this together. And then your second part of the question was about computational complexity. So the computational complexity, actually this slide is good to explain this, does not come from these 2 steps. That is the tapering and the computing the periodogram is on the same order as computing the Lomskargel periodogram. So this doesn't add any complexity. But the first step, which is computing the tapers, is where the computational complexity comes in. Back in the 1980s, they actually developed a method to compute these Slepian tapers on any irregular sampling that you want. But that method is very computationally expensive. And that's why we use spline interpolation instead, which is way faster. And what that means is that we actually get same computational complexity as using Lomskargel. And the interesting thing we found is that if we combine our method with PBJam, we get a factor 3 speed up because the variance of the estimate is very low compared to Lomskargel. So the peak tagging converges much faster. So at the end, you actually end up with lower computational complexity.
Yeah, great. Thank you.
Any other questions? I might ask one. Have you tested also in addition to the frequencies and how they compare between different types of power spectra? Also the measurement of say mode amplitudes and mode line width for p-mode oscillators, if they agree well, or if you in some scenarios will have difficulties because of reduced resolution from the tapering or these sort of things.
Yeah, so that's and again another good point. I will quickly pull up a slide to help with that. So yeah, as I'm showing in this particular slide where I simulated a time series and tried to see whether we can use our method to estimate the modes. So you can see here that in the end, you end up with a really good estimate of not just the frequency, but just by visually looking at it, you might see that you'll get a better maybe mode width estimate as well. We haven't really done that yet. We haven't really tested how our method improves mode widths, but we think that that is something that's an avenue we want to explore. And your second point was about frequency resolution. So as you can see here, as I increase the bandwidth to 4, now the peak is a bit more flat and the frequency resolution is a bit more. So this will affect your mode width estimate if you make your bandwidth too high. So that's something that will affect your performance if you keep your bandwidth too high. But that's why I said like the bandwidth, when your NW is 1, you're essentially using the same frequency resolution as what Lomskargel uses. So if you increase NW to 4, you're increasing it by order of 4 by T, or 2 4 by T. So you have to be careful about doing that to make sure that the mode bits are not affected.
Okay. Anyone else? Otherwise, I will ask another one. So have you tested also for, or do you know from this multi-taper or your other the NUFFT, how that's affected by potential heteroscedastic noise in the time domain or non-stationary noise, and how this compares to, for instance, using a weighted Lomskargel that can sort of take care of the heteroscedastic noise? How sensitive are you to systematics that are not removed and so on in the time domain?
Yeah, so stationary noise is another thing that I mentioned as a follow-up in our paper. So there's a lot of work done with multi-tapering and specifically dealing with stationary noise. So on the side of multi-taper spectral analysis, there's a lot of work that has been done about how we can use different versions of multi-tapering to deal with stationary noise better, better than Lomskargil, for example. So multi-tapering does help with that, with looking at stationary noise or kind of removing stationary noise, or sorry, non-stationary. But with respect to the NUFFT periodogram, so that's something we haven't looked at yet, is that how the two estimates compare. Right now, we see that they agree quite well with respect to each other in the kinds of Kepler time series that we're dealing with. But we expect that as the irregularity of the time series keeps increasing, the Lomskargil periodogram will start performing better. So there's a trade-off between how much irregularity you have and whether our method will work well in that case or not. So we still have to do some comparisons of when we reach that stage where Lomskargil should be used instead.
Okay, thank you. Any other questions before we end?
I see one in the chat about the bandwidth.
Yes.
So
That's
yeah,
that's a very small question, Arya. I understand that you say that you can increase the bandwidth. Can you explain me how you do that to increase the bandwidth with a factor of 4, for example?
yeah, so to increase the bandwidth, I just want to make sure, are you asking whether if I increase the bandwidth, does that affect K or does that affect the periodogram estimate?
It affects NW, I understand.
Mm-hmm.
And how do you do that in practice?
Okay, yes.
To increase the bandwidth.
So in practice, if you were to use, for example, the Python package that I've provided, you just have to plug in some bandwidth, and it's done generally directly. But internally, what I do is that as the bandwidth changes, again, I'll go to this slide. As the bandwidth changes, your tapers change. So here what I'm showing is 3 different tapers of order 0, 1, and 2 with bandwidth NW equals 2. So given some bandwidth, I essentially compute these tapers, which are dependent on the NW. And to compute this, it's this matrix evaluation that you need to do to compute the sequences. But essentially, it's the tapers is where the bandwidth goes.
Okay, so it's not related to the time basis that you have from the data. Maybe I don't understand the name. Okay, it's not related to the time basis of the data set.
So the bandwidth is related to these sort of time. So I'm showing here your original time series. Then I'm showing the individual tapers. And what I'm saying here is that you multiply your time series with a taper. So essentially you're using the thing that is done here is that instead of using a window that's a rectangular window, because your time is only in a finite duration, you're using the taper as your new window. And because the taper reduces sort of the importance of data near the edges, that reduces spectral leakage. And the bandwidth essentially will tell you how this taper time series will look like.
Okay, yes, okay, thank you very much. Yeah, thank you. It was a nice talk.
Thank you.
Okay, I think there are no more questions. It was a very interesting talk, and I think most of us will go read the paper now to understand it better. But thanks again, Aya, for a great talk, and I hope to see you all for the next Good Vibrations seminar, which will be on the 16th of November, where we have Rafael Reda, who will give the next seminar. But thanks for now, and hope to see you next time.
Thank you.